Hi, y'all. We're excited to have you here and want to welcome you to Flatiron School's Baseball Meets Data Science, Exploring America's Pastime with Bayes Theorem. My name is Corey Mickelson. I'm the event coordinator here with Flatiron School. A big part of my job is hosting these free events to give you an opportunity to meet some of our instructors and get a better feel of the Flatiron School experience. A quick reminder, we're using the chat as our main source of communication today, so make sure to switch that little blue button from host and panelist to everyone so we can all chat together. We have Alyssa here from admissions. You want to go ahead and say hi?
Yeah, hi guys. I'm Alyssa. I am a lead here on the admissions team, and I am happy to answer any questions that you might have, admissions related, really questions in general. I'll be kind of in the background here while you guys are listening to Greg. So if you've got questions, drop them in the chat and I'll try to respond as quickly as I can. But great to be here.
And we have Greg D'Amico here. He's representing our data science team. So go ahead and take it away, Greg.
All right. Thanks, Corey, and welcome everybody. Great to see a crowd out there. So I'm going to talk a bit today about baseball and about how data science might be relevant to baseball. Okay, so let me share my screen here and we'll get started. All right. Okay. Want to bring up the chat and okay. All right. Okay, so baseball meets data science. Well, there's a lot of ways that we might bring in data science to help us analyze some baseball statistics, but here is the way that I am going to think about it for today. Suppose that we wanted to figure out who are the best hitters and pitchers, and maybe also the worst hitters and pitchers in the history of Major League Baseball. Okay. How are we going to do that? Well, we're going to have to choose some metric, right? We need to sort of rank our players somehow. Most obviously for hitters, we would choose probably batting average. This is a normal, typical, good old-fashioned baseball statistic, right? Basically, how often does a player get a hit when he goes up to bat? For pitchers, this is probably a little murkier. There's a little more disagreement about how best to measure the quality of a pitcher. For today's purposes, I'm going to focus on a relatively new statistic called the WHIP. That's walks plus hits per innings pitched, right? So kind of the opposite of batting average for a hitter. It's how often does a pitcher give up a walk or a hit based on how often that pitcher has thrown on the mound, right? Okay, so that sounds reasonable enough, right? We could comb through all of our players and we could look for batting average, or if, as we'll see, we'll have to actually construct this statistic, but that's easy enough. And we can sort our players by those statistics, but there's still a remaining problem, which is that if we do that, right, well, these statistics, these sort of global statistics that we've called attention to here, these ignore the problem of players having appeared in very few games. And so in particular, right, suppose there's a player who appeared in just a couple of games and got hits, and so maybe went 3 for 3 in 2 games, has a batting average of 1,000, right? And yet that doesn't seem like we're going to be wanting to call that player the greatest hitter who ever lived, because it's such a small sample size, right? Corey, I just noticed I'm not sure that we're recording here.
It is, Greg. I see it recording.
Okay, great. Oh, now I see it. Yep. Okay, great. Okay, cool. Oh, I see. Gabriel is already suggesting a solution here. Establish a minimum number of plate appearances. Yeah, so that would be one way to do it, right? One way to do it would be to say, well, we're just going to throw out everybody who doesn't have enough experience in the major leagues. But what I want to do is something a little bit different. And this is where Bayes comes into the picture, Bayesian reasoning. Okay, and so here's the idea. What we're going to do is we're going to assume to start out that each of our players is an average player, right? And this is, in the language of Bayesian reasoning, this is going to be our what's called our prior. And so we're going to use Bayes' theorem here. Now, if you haven't seen this before, this can look a little intimidating. But here's the basic idea. Right, what we want to do is we want to think about the probability of a player getting a hit. Right, what's P of H? What's the probability of getting a hit? Well, what we want to do is we're going to start with this prior, right? This prior is going to be the same for every player. And to choose this, we'll just think about, what is an average? What is a typical batting average across all players? Just choose that for our prior. And then the idea is we want to calculate this. What is the probability of H given E, right? What is the probability of getting a hit given some information that we've learned about this player? What is that information? Well, it's going to be the player's career numbers, right? What is the probability that a player gets a hit given all of the weight of this player's career, right? Given the career statistics that we have in front of us. And so the idea is, right, if a player has not very much experience, then the prior is going to sort of dominate this calculation, right? The batting average that we start with, that we assign everybody to begin with, that thing is going to dominate this calculation. But on the other hand, right, if we have a player who has a big, long career, then for that player, the career numbers will dominate, right? Bayes' theorem basically tells us how to update our beliefs about something, right? In this case, what's the probability of a player getting a hit, a particular player getting a hit, right? I have some starting belief about what that probability is. That's P of H. But then I have some evidence that comes in, right? And I put together these numbers in this way. This is just a straightforward theorem of conditional probability. And so what I come out with is a way to calculate an updated belief about this, right? What should my new belief be about the probability of this player getting a hit, given this evidence, given this information, given, in our case, the player's career numbers? Okay. And so again, for a player with lots of experience, the career numbers will dominate, right? The prior will sort of be washed away because we will have all sorts of reason to update our belief about whether that player is average, right? If the player is, for example, really good, right, then those career numbers will dominate that calculation, and we'll have an updated version, an updated belief about this player's ability to get a hit. On the other hand, players with little experience, the prior will dominate. We won't have much reason to update our belief at all. Okay. So that's the basic idea. We're going to try this with batters, and we're going to try the same thing, more or less, with pitchers. Okay, so let me move over to my code here. Okay, so I've got a Jupyter notebook here. This is standard tooling around here at Flatiron School. Basically, this is a really nice way of running Python code, if you haven't seen this before. And what we're going to do is we're going to be able to run some code, see the results of that code. We're going to be able to manipulate a large data set that has a bunch of information about baseball players. And we'll be able to sort of see the results of our work as we go. Okay, so to start, I'm just going to bring in some data here. If you're interested in this data set, oh, it looks like I need to update this link. But there's a guy called Sean Lehman who has a big baseball archive of statistics. I think if we, yeah, okay, so we'll just have to we will update this link for you. Also, you can check out the data link on my GitHub page where this is being run from. Okay, so hello, come back. Okay, now I need to go back to my, okay. So let's bring in some tools here. So I'm going to bring in, these are just some standard tools in Python to help us do some calculations. Okay, so there's a data set that I'm calling batting here. It looks like this. Okay, and it looks like, right, if you sort of stare at this, it's a little bit hard to see immediately what's going on. But across the top, I've got my baseball statistics here. Okay, so here I've got games, at bats, runs, hits, and so on. I have a player ID here. Okay, this is a little bit coded here. So there's some kind of way of constructing this player ID given a player's name. I've got a year. And I notice, right, these years are 1871. So it looks like this data set is arranged chronologically. Okay. If I want to check out the columns, and I can just grab those and see what they are. If I look at the back end of the data set, right, so you can see this one goes up to 2016, right, and I've got still the same columns here, games, at bats, runs, hits, and so on. Okay, so just checking out a player at random here, I happen to know that Pete Rose's player ID is Rose PE01. Okay, so I can just grab that. Right, notice the indexing on the side here. Right, this shows us that these rows do not appear consecutively in the data as it stands, right? Because again, the data proceeds chronologically. So all of the players who played in 1871, all of the players who played in 1872. But with this tool called Pandas, it's easy to grab all of the Pete Rose years, right? And so I just have those in front of me. I can look at his stats year over year. Okay. Now, what I really want to do is I want to think not about an individual year for a given player, but I want to think about the totals, right? The career totals for each of my players. Okay. So I'm going to do a few manipulations here that I'm not going to worry about for now. Okay. And so what I want to do is I want to group my data. Right? I want to group my data by the player ID. And then I'm just going to sum over all those totals. Okay. So for example, right, if I look up Hank Aaron now, right, I have this new data frame called players. And in players, right, this thing is grouped all together. So there's now just one row for Hank Aaron. And it's not, right, any particular year, it's his totals for his career. Okay, so you can see here, Hank Aaron got 3,771 hits in 3,298 games. That's pretty darn good. Okay, 755 home runs. Right, this was a record for, I forget, 50 years or something. Right, 2,297 RBI. I can see all these total statistics for Hank Aaron. Now, one thing I notice is I don't actually have a batting average column here. Right, that doesn't actually exist in the raw data, but it's easy enough to construct. Okay, especially again with my Pandas tool here, all I have to do is grab the hits column, right? Grab the at bats column, divide the one by the other, and I will have a batting average. Okay, and I'm just going to add this right into the new data frame. Okay. So I'm going to run that calculation, and then I'm going to check out, here's Pete Rose again. Okay, and you can see I've added this column at the end, average, and it looks like Pete Rose's career batting average was about 303. Okay, and if we want to, we could check Python's math. We shouldn't have to worry about such things, of course, but it looks like Pete Rose got 4,256 hits in 14,053 at bats. Okay, 302,853, and that's exactly what we have here. Okay, if we wanted to, we could add a slugging average column. I'm not going to worry about that for now, but clearly with this kind of tooling with pandas, it's easy to construct all the stats that we might want, right? Given the columns that we have, it's easy to create new columns. Okay, cool. So let's see if we can find the worst hitter. Okay. Now, here I am. I'm sorting my worst hitters here. And if I just run sort values on average, well, I get that sorted, right? And you can see I've got some zeros and so on. But again, this is where we run into the problem, right? Because I haven't yet taken account of the fact that some players have very little experience, right? And I don't want their little experience to sort of screw up my ranking here. If I'm really looking for the best player, right, somebody who got one hit in one at bat ever, I don't want that guy to count. And if I'm looking for the worst hitter, somebody who got 0 hits in 2 at bats ever, I don't want that guy to count as the worst, right? It affects sort of both ends of my ranking here. So again, right, this is now where we bring in Bayes. And so what I'm going to do is I want to choose, again, some Bayesian prior. I want to choose some average, batting average, to use as a prior probability distribution. Right? Then take the weight of the player's career as the evidence that will allow us to update our belief, update about our probabilities, update our batting averages, right? To something that's probably more representative of how skilled the hitter really is. Okay. Okay. Now, in this particular case, there's a really nice thing that happens. Getting a hit is a binary process, right? The player goes up to bat, either the player gets a hit or the player doesn't get a hit. And so that means that we can use what's called a beta binomial distribution. And the beta distribution is what's called a conjugate prior for a binomial likelihood. Right now, this notion of Bayesian conjugacy is somewhat complicated, but what it means for us here is, here's the bottom line. Okay, this is pretty neat. I can simply add a player's career hits and at-bats to the prior's hits and at-bats, and that will be an accurate calculation for the posterior, right? This will be a quick way to solve Bayes' theorem. Right? So all I have to do is take the player's existing hits and at-bats, figure out what my prior is going to be, add that to all of my players, and I will therefore have posterior calculations for all of my players. Okay. There's some fussing about what an average batting average is in the major leagues. And you might sort of worry about, well, should I count the players who play longer? Should I count their averages for more or whatever? But typically most people, when they're thinking about this, come up with something somewhere around 260 as an average batting average, right? So somewhere around 26% of the time, a typical batter will get a hit when they go up to the plate. Okay. So I'm going to just model this, right, and say, all right, well, if 260 is my starting assumption here, right, then what that means is my probability distribution looks something like this. Okay. So if I'm thinking about, right, what does it look like? How would I measure the probability of a player getting a hit? Well, right, typically it's somewhere around 26%, 0.26. Okay. And so, does that mean that a player, could bat 400 for a day or for a week? Well, yeah, but that's not very likely, right? The most likely thing is that they bat about 260. Okay. Okay, so here is the the major step now, right? I'm going to add a new column. This is going to be called the maximum a posteriori column. And what this looks like is I'm just going to take the player's hits and I'm going to add 26 to it, right? I'm going to take the player's actual at bats and I'm going to add 100 to it, right? 26 out of 100. Okay. There is something sort of funny going on here. So I just want to pause and think about what Bayesian reasoning is allowing us to do here. So in a typical and an ordinary stats 101 sort of context, right, you're given the distribution, you're given some probability distribution, right? Like maybe you're told that there's a die that you're going to roll and it's uniformly weighted, and so that you have a uniform probability distribution. And then as the student, right, you're supposed to calculate, okay, what is the probability that, you know, I get a 3 on the die, or I get an even number on the die, or whatever. With Bayesian reasoning, we can also flip this around. Oh, I just noticed that Mike sent out a link to some of this data. That's great. Right, with Bayesian reasoning, you can also often flip this around and say, all right, well, here's what happened, right? I rolled a 3, or I rolled a die 5 times and I got, you know, 2 3s and 2 4s and a 1. Given that data, given that response, given that fact, right? What is the likeliest probability distribution that describes the behavior of this die? Right? That's in effect what we're doing. We're saying, well, you know, I could say, here's the probability distribution, you know, what's the chance that he gets a hit? But I'm saying, here are the data, right? This is what the player did. What is the likeliest probability distribution that underlies my data here? And crucially, in order to do this calculation, right, what's very sort of distinctive about Bayesian reasoning is that you need this prior, right? You need to have some prior belief about what the probability distribution is. And so again, naturally, we just choose an average, right? We assume that the player is average, and then ask, okay, is that a likely probability distribution for the data that we see? Okay. Okay, so we're going to try 26 out of 100. We're going to experiment with this in a little bit, right? We said that the average is 260, but that doesn't necessarily mean we should choose 26 hits out of 100, right? We might choose 52 hits out of 200, or 2.6 hits out of 10, or something like that, right? So we still have a choice. We've chosen the percentage, but we still have a choice about how many hits and how many at-bats to use. Okay. Okay. So just like that, I've added this column to our data set here. And so now I'm going to sort these values. Okay. Notice that when I run this sort values function here, I have a choice about whether to sort them in ascending order or descending order. Okay. So if I'm saying ascending equals false, right, then I should get the best players at the top of this list. And if you know much about baseball, then you're probably not surprised to see Ty Cobb here appearing at the very top of the list. Okay, and it looks like Ty Cobb's career average was around 366. Okay. And I've got this new column next to it now called MAP. And of course, it's going to be a little bit lower than that, right? Because we started with this idea that Ty Cobb is an average hitter. And of course, the weight of his career numbers are going to say, no, that's actually not very likely at all that he's an average hitter. It looks like he's more like a 365 hitter. Okay. And that 365, right, that is the highest among all of our players that we have here, because this is the way that we've arranged our data here. Cool. Okay, I'm going to do a couple other manipulations here that are not important for now. Notice, right, if I had a player that had a perfect batting average, then, you know, certainly that player must have had a very small career. if they went 1 for 1 in their career or 3 for 3 or something like that. And if I look for, right, where the average was maximized, right, then I can see that, right, even though they had a high batting average, right, and here's a batting average of 1.0, 1.0, 1.0, right? So this guy went 1 for 1, 1 for 1, 1 for 1, 1 for 1, right? But their new adjusted averages are 267, right? Because we just don't have enough evidence to sort of upset our prior starting belief that these guys are probably average hitters, right? If George Abrams, I think his name is George Abrams, if he went 1 for 1 in his career, right, is that enough evidence to make us believe that he is not an average hitter? Well, no, not really, right? He's probably a pretty average hitter. This is a little bit higher than our 260, but not by much. Okay. Gabriel says, why are strikeouts not a major part of determining hitter's worth? Yeah, we could certainly fight about this. So, you might think that, as you put it, contact outs are more valuable than strikeouts. This sort of depends, if nobody's on base, then it doesn't much matter. Sometimes outs are productive in the sense that they could move runners over or bring runners into score. I'm not sort of worrying about those complications here, but you could try to bring that in if you wanted to. Okay, so what I want to do now is I want to think about different starting assumptions, right? We're still going to have a 260 batting average, but we're going to experiment with different numbers of hits and different numbers of at-bats. And so for this, I'm going to create a little function here. This is called average prior. Okay. And what I'm going to do is I'm going to start with the player's actual hits, start with the player's actual at-bats, and then I'm going to add in, right, a user-determined number of hits and at-bats as my prior, right? So if I set H equal to 26 and AB equal to 100, I would get exactly the ordering I just got, but this function means that I can put in whatever I want, okay? And I'm going to grab the top 10, and I'm going to look at the player IDs for those top 10. Okay. Okay, so let's just run this function a bunch of times. So I'm going to say, all right, well, let's look at bats that start at 10 and go all the way up to 5,000, counting by tens. Right? So we'll try 10 at bats, we'll try 20 at bats, we'll try 30 at bats, all the way up to 5,000 at bats. And what am I going to choose for my number of hits? Well, of course, I'm just going to take that at bat number and multiply by 0.26. Okay. Richard, yes, this notebook will be provided. It's on a GitHub repo that you'll have access to. Okay, so still 26%, but just varying numbers of at-bats. Okay, so let's just collect all these together. Now I've got a big list of, what's the word for a group of 10? A decade or a decad or something like that. A big list of decads of players. Okay, let's look at the first set of 10 in our list. Okay, if I just choose 10 at bats, right, then the worst hitter is this guy called Ron Herbel. And, probably he wasn't a very, very good hitter, but you probably also 10 at bats is really not enough as a prior, right? It doesn't seem like we should count, just 10 at bats as sort of sufficient evidence that this player is not a good hitter, or a good hitter for that matter. We could go up a little bit. All right, so here's 169 at bats. Sorry, this is not 169, but this is 170th in our list. So this is actually 1,700 at bats. Here is 1,710 at bats. Okay, and if we want to be even more precise, we find that at precisely 1,705 at bats, the worst hitter switches from Bob Buell to Bill Bergen. Okay, so here is 1,704 at bats. Plugging in our function, you see Buell is at the top. Once we get to 1,705, Bill Bergen is now at the top. Okay. Here is what Ron Herbal's career looks like. Okay. You know, not a lot of action here, but in 1964, he went 0 for 47. In 1965, he went 1 for 49. Right? It's pretty bad. Pretty bad. Here he went 0 for 64. Okay. Now, you know, is he the worst hitter of all time? Well, probably not, because he was only the worst when we had this really small number of at bats to start with. Okay. Okay. Here's Dean Chance. This is another player's name who showed up early on. Right. 0 for 5, 4 for 65, 12 for 80. Okay. If we want to look at his career, right, 44 hits and 662 at bats. Pretty bad. Okay. Here's Bob Buell. Okay. Bob Buell's career. 76 for 857, right? Career average of 0.089. By our calculations, right? By our Bayesian calculations, he's got an adjusted average of 203. Okay, pretty bad. So we said, well, suppose he's 260, and the Bayesian calculation said, I don't think he's 260. I think he's more like 203. And that's a pretty significant drop. Here's Bill Bergen. Okay. Played for my beloved Cincinnati Reds for a few years back in the early part of the century. And career totals for Bill Bergen, 500 hits, 3,000 at bats. Okay. Actual batting average career of 170, but you know, by our adjusted calculation, 203. Okay. Quick aside on the best hitters, right? So this function that we're using up here, sorry for the scrolling, but this function that we're using up here, this is using the same old function of, right, the same old method, as it's called, of sorting our players by the stat by which we want to sort. And in that function call, right, we can again set ascending to false or to true. We've been setting it to true. It's true by default. Right. And so that means that when you look at the top of the list, you'll see the lowest numbers, i.e. the worst hitters. But if we wanted to, right, we could just tweak that and say, well, actually, let's set ascending to false now, and we'll find the best. Okay. So here, what I need to, I'm just going to adjust this function here. Okay. Comment this out. All right, so now we'll set ascending to false, just adjusting this function slightly, but now we'll see the best instead of the worst. And so if I run this code here, okay, so I've got, again, lots of different lists here. First 10, second 10. Already in the third set of 10, I see Ty Cobb at the top. Ty Cobb, Ty Cobb, Ty Cobb. Okay. So for almost all values of at bats between 10 and 5,000, you can scroll through this if you want to, but I encourage you just to take my word for it. All right, Ty Cobb is the best hitter by almost any metric at all. Okay, you can check out his page on baseballreference.com here. All right, and if you look at his career numbers, right, he's got a huge wins above replacement here. 4,189 hits. Okay, so just terrific career. And notice also terrifically long career, so that, you know, it was sort of clearly going to outweigh this default starting assumption we made of supposing that he's an average hitter. Okay. Now, one complication here is that you might say, all these players we're looking at their hitting stats, and some of these players are pitchers, right? And pitchers, well, those are sort of specialized players. We kind of give them a bit of a break when it comes to hitting. We don't necessarily expect them to be good hitters in the same way that we expect non-pitchers to hit. Right. And so what we might want to do is to filter out our non-pitchers. Sorry, filter out the pitchers so that we just have only non-pitchers that we're looking at. Okay. And so maybe what I really want to know is who's the worst hitter who was not a pitcher. Okay. Okay, so here, all right, I've got my list. Here's my, this is what my, oh, sorry, I want to go back to the worst. That's back to being the best. Okay, I'm going to comment that out, rerun that. All right. Okay, so here are my worst hitters again. And I've got several pitchers in here. So Ben Sheets, Dick Ellsworth, all these guys are pitchers. Right? Sandy Koufax shows up. Sandy Koufax, that's a Hall of Fame player. Not, of course, as a hitter, but as a pitcher. Right? If we change our numbers, right, we'll encounter more pitchers. Okay. How are we going to filter them out? Well, here's one way to do it. We'll bring in our pitching data. Okay. And what we're going to do is, right, we'll just look for the hitters who have no pitching record at all. Right. So if there are people who appear in the hitters data and not in the pitchers data, right, that would be a way of guaranteeing that they were never pitchers. Now that's a little bit crude. You might say, well, we want to include them if they hit through a few pitches, every now and then, but we'll just go with pure batters for now. Okay. And so what we're going to do is we're just going to mark in our hitters data. We're just going to mark whether they ever also pitched. Right. And so if the batter does not appear in the pitching data, right, then we'll say 0 and otherwise 1. Okay. Just going to add this as a column. And so now what I'm going to do is I'm just going to grab, if we want to see what this looks like. Okay. It looks like this. So I've added this column that says no pitch, right? It's just 1s and 0s. Okay. So what I want to do is I want to just grab the ones where no pitch equals 0, and we'll redo our calculations here. All right. Same kind of thing. If I actually look at this, it's a big long list here. Okay. But I notice that before long, right, here's my old friend Bill Bergen again. And in fact, he shows it pretty early and persists. Right. So Skeeter Shelton shows up at the very beginning. Ed Gastfield shows up at the very beginning. Mike Jordan shows up a little bit later down here. But Bill Bergen, whom we already saw because he was showing up even before we eliminated the pitchers, right, seems to be our winner or our loser. And if we find the exact number of at-bats where Bergen comes to the top, or bottom more like, we'll find that it's at 133 at-bats. Okay, which isn't really, it seems like enough to make a determination. It's not a huge number of at-bats. That's really only part of a season. It's a couple of months. But if we count, right, 133 at-bats or more, Bill Bergen will count as the worst hitter in the history of the major leagues. Okay. So that's our sort of Bayesian exercise just notice a couple things again, right? We're looking at batting averages. We had to construct that stat, but that was easy enough. And then the key thought was, well, we don't want to just look at pure batting averages because of these discrepancies in career numbers, right? Career experience. But if we use this Bayesian trick, right, we can just kind of set a prior, assume that everybody is average, and then let the weight of the player's career affect our judgment about whether they're average or not. And if we do that, right, then that calculation will say, you know what, this guy, Bill Bergen, he is almost certainly not an average hitter. And in fact, he is very likely the worst hitter in the history of the major leagues. Okay, I've got another notebook here about pitchers. I'm not going to go through the whole thing because the idea is, you know, totally the same, except that we just work with, okay, let me zoom things getting in the way. Right, we just work with a different stat. So we work with WHIP instead of batting average. And so if I bring in my pitching data here, right, I won't go through this, but we need to add a WHIP column again. Okay, there's a little bit of a complication because in the raw data, they have something called IP outs. So this is, you know, not straight innings pitched. This is basically number of outs pitched. And that's useful here because innings pitched are often, you know, they often come in numbers like, you know, 10 1/3 or 147 2/3. And those thirds can be awkward to deal with. Hence, we deal with this innings pitched outs. And so to construct the WHIP column, we just need to add that factor of 3 back in. Right. Okay, so same sort of thing, make a prior assumption about WHIPs, right? You might want to look for pitchers after 1900 because the rules of the game changed so much after 1900. You might also want to distinguish between starters and relievers. Okay, and if you do all this stuff, right, well, lo and behold, you find that Dick Wake comes out as the worst starter. Stu Flythe comes out as the worst reliever. And as for the best starters and best relievers, Addy Joss may not be a familiar name. This is sort of an old legendary player here, but had an excellent WHIP over his whole career. And for relievers, Koji Uehara is very likely the best reliever, who's actually, you know, a very modern day player. Robert's asking about positions, players who pitch or two-way players. Yeah, that's a good question. We don't have a good answer to that right now. So, you know, if obviously we were looking for our worst hitters, we would, or best hitters, and we said, well, let's not include pitchers, Shohei Ohtani would get cut out of that conversation, right? So to deal with him, we would need something a little more sophisticated to, you know, so probably we would say, well, okay, what we really want is a sufficient number of at-bats, maybe a sufficient number of at-bats per year or something like that, or even per game, because, you know, the pitchers tend to be, you know, having very few at-bats per game or per year. Gabriel's asking about the hitting net worth formula. So this is total bases plus walks plus hitting. Yeah. So that's an interesting stat too. I think we could do much the same thing, right? So again, for players with very short careers, you know, that calculation that adds up bases, walks, hit by pitch, strikeouts, right? It's probably going to be a little misleading because for small sample sizes, the player is probably not performing, right, with according to how good or bad that player really is. And so the whole point of the Bayesian, you know, setting the prior and recalculating is to try to smooth that out. And so I think you could try it for that stat for the hitting net worth formula and see what you come up with. You know, would Ted Williams be at the top? Would Ty Cobbs be at the top? You know, because you're using total bases instead of just hits, right? The power hitters are sort of floating to the top a little bit. Ted Williams and Babe Ruth hit a bunch of home runs. Ty Cobb did not, right? So they're coming to the top a bit more. But I encourage you to try this very same trick with that. I think it should work. All right, so I'll leave it there. Happy to take any questions, and thank you all for coming.
Anybody have any questions that didn't get answered during the event?
Very welcome, Darius.
All right, Corey. I'm here.
You're here. If anybody has any questions for Alyssa, if you have any questions about the program, feel free to drop them in the chat. Now's the time.
Brent says, if you wanted to include more than one metric, like WHIP and ERA, how could you incorporate both? Yeah, that's a good question. So I think, Brett, probably the best thing to do would be to, I think my first step would be, let's do it according to WHIP, let's do it according to ERA, and then just sort of look at the different lists that get generated. You could try to create a combined metric, but then, probably there would be some unclarities about how exactly to do that. I think the Bayesian approach should be the same. I think the trick would be in, what the proper nature of the combination is. And so probably I would do them individually and then just sort of try to compare them side by side and see if I can find a pattern.
Let's see, it looks like there's something in the Q&A from Robert. In the analytical community, we use metrics like expected batting average. If we don't have raw values like exit velocity, launch angle, etc., can we use Bayesian approach to calculate an expected batting average?
Sure. I mean, the Bayesian technique is sort of fully general, right? I mean, it's the theorem itself. There's nothing controversial about the theorem itself, right? It is just a theorem of any normal probability calculus. What is controversial is sort of thinking about what the theorem represents and imagining it as representing, this is how we properly update our beliefs. So the sort of orthodox Bayesian will say, right, probabilities just are reflections of our rational degrees of belief about a thing. That is certainly more controversial, but the theorem itself is fully general. Mike is asking about the correlation between WHIP and ERA. Well, there is a correlation. So, there would almost, if we did these side by side, right, then we should expect the list to be somewhat similar. Of course, they're not perfectly correlated because, sometimes you give up a bunch of hits and yet nobody scores and so on. So, there are different strategies for dealing with that correlation. You might try to, I mean, this is partly why I'm recommending to do them separately, right? Because then you won't get any sort of cross-pollination that might affect the analysis.
Alyssa, it looks like there was a question in there for you as well. Somebody's looking for an email available for more questioning.
Yes. If you do have more questions, feel free to email admissions@flatironschool.com, admissions plural. And we can direct your questions to other spaces if you guys have it. There we go. Yep. Thank you. And we can direct your questions however we need to, or see if one of our admissions teams can also answer those questions for you guys.
And I dropped a link to the website in there as well, because several resources on there, as well as syllabuses or syllabi for all of our different programs. Did anybody have any other questions?
Oh, I see there's a question about the law of large numbers.
Okay.
That's a good question. So does the law of large numbers apply in determining the worst pitcher? So I would say this is sort of very relevant to our starting choice of the prior, right? So Typically average players will reveal themselves as average given enough at bats. Good players will reveal themselves as good given enough at bats, and so on. And so this just means that we need to be, careful about choosing the right prior to make sure that the evidence, the career, has the proper effect on how we should update our beliefs.
I also just dropped a link to our YouTube channel in there. If you want to watch any of our prior events, you can go in there. We have everything from data science, cybersecurity, software engineering, and product design, as well as some of the panels that we've had with alumni and other people from the field that we've brought in for guest speakers. Thank you, Mary. Okay, well, thank everybody for coming in today. If you have any questions, we did drop the link in there for info at admissions@flatironschool.com. You can also go to our website, and we will send a recording of the presentation within 3 business days. We'll go ahead and include Greg's GitHub in there, and then all of our resources for today. Thank you all, and have a wonderful afternoon. Bye.
Bye.